let's get started. So I'm Christiane Helling, as was already introduced, and I thought I give you a little bit an introduction of what my research is and what we are doing in Gradcu. So I'm right now at the Space Research Institute of the Austrian Academy of Sciences, and this is actually our building, which looks much less colorful than your environment here. So, and we also don't have a river flowing on our banks, so yeah, you can't have it all, right? Okay, so let me just spend the first moments to introduce actually the institute. So we are the Space Research Institute in Austria, and this means we are involved in loads of space missions, and this is not just something we have started now, but this is a whole tradition going back to the beginning of time almost. So the institute is now 50 years old. So we are involved in 24 active and future space missions, and we have here listed some of them. So we are involved in those studying the near sun environment, then plenty of missions that study the interaction between the sun, the solar wind, and our Earth atmosphere and magnetosphere. Then we are involved in a mission in Bepi Colombo studying Mercury, the innermost planet of our solar system. Then in missions traveling into the outer solar system, so this is Jupiter, and here is JUICE. And then JUICE is a space mission. Then Comet Interceptor to be studying a pristine comet to study the origin of the solar system. And in recent years, we have included more and more missions that actually study extrasolar planets, so planets outside our solar system. And I think one point which I really want to make is that our engineers are super proud that their instruments have literally visited almost every object in the solar system. And now I'm not an engineer, I'm a theoretical astrophysicist, but I can feel they're proud. So our institute has 8 research groups, and we work in a particular fashion. So so each of our instrument developments needs to be rooted into a scientific research question. So the scientific research question drives the development of our instruments. Then we conduct measurements, and then in the institute we have under one roof the scientific analysis of this data. So, and this now also explains our research groups. So we have 3 research groups working on extrasolar planets. So my own research group, Luca Fosatis and Peter Woidke. Peter Woidke is sitting over there. Then we have 2 research groups working on solar system objects, and then we have 3 research groups working on technology development, one on board computer, one space magnetometers, which very well links to space plasma physics, and then satellite laser ranging. So now I have a question. Who of you has a natural science background? Okay, perfect. Then I don't feel anymore like talking too much into detail. Very good. So this is the timeline of our space mission Armada. So it only starts at 2000, and some of us have heard about Cluster. Oh, this is in German, I just see. Cluster is looking at the interaction of the solar wind with the Earth's magnetosphere. And here we go further on. Here we are in 2026. And here we are about to witness another space mission launch. This is SMILE, and the next on our chart is actually is an exoplanet mission, is Plato. And here I'm now showing all the missions that we are involved with, and which study extrasolar planets. So there is Cheops, there is Plato to be launched, there is hopefully new Athena. We hope that this is turning to help us with exoplanets, and then there's Ariel. So there are also the flagship missions from NASA and from ESA, where we are hoping to contribute to instrumentation, but this has to be seen. Okay, so this is now my gateway into the topic. I will from now on leave all the introduction to the institute. You are more than welcome to ask me, but I will now move towards exoplanets. Yep.
Yes, speaker.
Is there a way to make it louder? Then I just move towards you.
Who's there?
Yeah, maybe you come a little forward. The point is, the louder I shout here, the more echo I have here, and so these people get echo death. Let's see. Okay, let's probe, and you give me a thumb up or down. So, right now we know about the existence of more than 6,400 extrasolar planets, which orbit in more than 4,800 planetary systems. The realization to make is that these exoplanets are located within our immediate neighborhood, right? So that means we only know a very little part of our galaxy with respect to the exoplanets. And what is also important to realize is that none of these planets actually resembles what we have in our solar system, nor the planets, nor the structure of the solar system. So we never have found a solar system twin, nor a solar system planet twin. Why is that not entirely surprising? Well, we know that such a spiral galaxy as our own Milky Way has about 400 billion stars. Maybe 100, maybe 700, depending whom you are talking to. But if each of these stars hosts just one planet, that means our Milky Way galaxy, our spiral galaxy, must contain at least 400 billion planets. So, and I mean, if you are looking around this room, then none of us is the twin of the other. It is very seldom that this happens, right? So we shouldn't expect it for exoplanets to happen. Exoplanets are therefore very diverse, and this is a very blurry picture, and it's on purpose very blurry, because we know as of yet very little about exoplanets. We know that they exist, and we have started to characterize some of them. And I will lead you step by step through what we are actually contributing to this characterization. But let's do something. Oh, there we go. Let's first talk a little bit about the diversity of exoplanets. So as I said, we know about a little bit more than 6,000 exoplanets, extrasolar planets, but we only know for a handful of them the radius and the mass. And this is what I'm plotting here right now. So on the y-axis, you have the planetary radius in unit of Jupiter radii. On the x-axis, you have the planetary masses in units of Jupiter masses. Color-coded, we have we have the host star's temperature, which means the hotter the host star, the redder this blob actually gets. So let's see what else we see. Here we have have Jupiter. That means here this point would be where Jupiter is located. This line, this horizontal line, would be all the planets with Earth radii. So what you see is that we do not only have Earth radii, we do not only have Jupiter, but we have a whole lot of other stuff. Up here, that's what we are calling gaseous planets, and again, they are not just all sitting at one blob where one Jupiter radius and one Jupiter mass is, so there are plenty of gaseous planets. And down here we have the rocky planets, which basically indicates we know about rocky planets. But what I want you to realize is that down here is what we know from our solar system, from the inner solar system. So we have the inner 4 rocky planets: Mercury, Venus, Earth, and Mars. And then we have the outer 4 gaseous planets in the solar system. But from exoplanets, we suddenly realize there is an entire group of planets that does not exist in our solar system, and that's what we are calling mini Neptunes or super Earths. It's very, very, very ingenious, this naming. It literally means they are smaller than Neptune and bigger than Earth, and we actually don't quite know how they formed. I mean, we're getting more and more ideas about how this actually works, but this is a new class of objects that has been discovered. So, there we go. What we also can now do is, for those planets for which we know the masses and the radii, we can do another game. We can do our first characterization game for the rocky planets. Here we have radius on the y-axis again, this time in Earth radii. Here we have masses in Earth masses. Color-coded are the dots again according to their temperature. This is not too interesting right now. What is interesting is that we have certain lines which indicate billiard ball spheres of homogeneous composition, of a homogeneous density, which are 100% iron 100% water, which are a combination of molecular hydrogen and helium. What it tells you is that there's a whole spectrum of material composition alone in those rocky planets that have been known at this particular time. What you don't see, I guess, what you don't see at the last row, in the last row of this lecture hall now, is that there are pretty large error bars on this plot. So these error bars are sometimes as wide as half of this plot. Nevertheless, this is the first start for doing a planetary characterization, and I want to do a game with you. Who knows the definition of the density? The front row is not allowed to answer. Definition of density?
Yes.
Thank you. Volume for a sphere?
That.
Volume for a sphere?
Our.
Okay, I assume we all know this. Okay. Oh, there we go, sorry. Yeah, brilliant. So, what I'm showing you here is that we can observe the mass and the radius, and if we assume that our planets are homogeneous spheres, we can actually calculate a bulk density. And with such a plot, we already get the first idea that the bulk densities of these rocky planets alone are very different. And why is this interesting? Well, it is interesting because we now know that we get from Plato much higher precision radii for the planets, because Plato will characterize the whole star's radius to a precision of 3%, which means we get the planetary radius precision to a precision of 3%. And on the other hand side, if I know the density of the planet, I already get an idea of where it may have formed and what kind of atmosphere it may have had. So this is a very simple exercise of just using masses and radius for this one. Now, if we do have the radius and the masses, we can do this exercise not only for the rocky planets, which we can talk about as of billiard balls, but we also have gas giants and mini-Neptunes, as I just said. And now we have on the y-axis the planetary bulk density, and on the x-axis the planetary mass, and now again in Earth masses. If you let your eye wander, so this is a logarithm of 10, that means at 0 we have the Earth mass sitting, and there we go. This brown square is exactly our Earth. So then which square would then, which planet is represented by that square here? Mercury, right? And then we have Venus, and then we have Mars. Right. The beauty of this plot is actually that we now suddenly have two branches. Initially we had a whole point cloud, right, of in our rocky corner. Here we have two branches, where we have here the super Earths and the mini-Neptunes and the gas giants. And you see, we are diving more and more into characterizing planets based alone on the fact that we know their masses and their radii. But what you also see here, there are gray and blue dots. The blue dots are those for whom we know the radii to a very high precision, 5%, and the masses to 10%. And the gray dots are all those planets for which we don't know these values with a particular high precision. So that's all fun, but what we actually would like to know is how can we, if we can combine a global parameter like the density or the mass with something what we have every day, weather or climate. Let's see what we can do. So, for this, I now would like to dive a little bit more into the complexity of exoplanets. So far, you have perceived from me exoplanets as a dot, a spherical symmetric something, which has a homogeneous bulk density that we can determine by the radius and by the mass. It's all wrong. Exoplanets are far more complicated. So we have an interior, which may be rocky or which may be gaseous, but they are surrounded, most of them are surrounded by huge gaseous envelopes. We can call them gaseous envelopes or atmospheres, depending on their evolutionary state. They may clouds form. Planets may or may not have a magnetic field. We have no way, as of yet, to measure the magnetic field of an extrasolar planet. We can go to our solar system planets and stick a magnetometer and actually measure the local magnetic field strength, but that's about it. So then our exoplanets, they are in a galactic environment, right? They see galactic cosmic rays, for example, then they orbit their individual host stars. So they have completely different radiation fields, so it may be an F, K, G, K, or M star. And all of this affects what we actually observe as astronomers with our instruments. So therefore, our research questions in my research group is then, how does the weather and climate change for exoplanets throughout the galaxy? And now you also see why I said galaxy, right? Because it depends on where our planetary system sits. It depends what the stellar neighborhood is. If they are in near a star-forming region or not. If a supernovae explodes or not. So what is the high energy radiation environment? So how do clouds form in different exoplanets? Okay. And then also, how does the high energy environment affect the chemistry? This is all what we want to understand, and we do this by using space mission data from Cheops, JWST, hopefully soon from Plato, then Ariel, and maybe also from New Athena. New Athena is a concept for a, actually not a, is a mission, is a sorry, this is German, is an X-ray observatory, is an X-ray space observatory, hopefully to be flown. We will see. So, in order to understand these complex systems, we are building virtual twins in order to predict the weather and the climate on exoplanets. We do this by building physical models. We describe the wind, which is hydrodynamics, Navier-Stokes equation for those who are more like this more. Then we have to model how clouds form, how rain falls, how lightning may appear. And then we have to model the impact of the host star. And all of this, of course, happens in a planetary system, which means the distance from the host star will affect the atmosphere themselves. We convert this into a mathematical model. I would expect most of you are aware of this. And I'm not putting up the entire mathematical model. I'm only showing you some of the equations. And these are some of our cloud formation equations, but what you may want to be aware of is, or what you may be able to see is that these are actually conservation equations, right? They have the structure of the Navier-Stokes equations. So here we have the time-dependent term, you have the advective term, so something is moved with a certain velocity, and that's the bulk velocity, what we're calling the gas velocity. And then we have a whole set of source terms. And here's actually where the beauty starts, because here enters our physical understanding for phase transition. I'm not going into the detail. I'm more than happy to talk to you about this if you are interested in. But I think the point I want to make is we are not just doing approximations or something. We are really writing down the mathematical equations to describe our physical understanding. So from now on, no equations, only boxes. Our virtual observatories, our virtual laboratories are used to, are helping us to describe the atmospheric physics and chemistry. And we have now coined this as the IWF, Institut für Weltraumforschung, Space Research Institute, modeling pipeline for extrasolar gas giants. What does it do? So this is our physical and chemical modeling. Here on your left-hand side, we have the model that describes the global atmosphere structure, the thermodynamics and hydrodynamics. We basically get the entire, we calculate the entire temperature, velocity, and pressure field. Use this as input for our cloud formation, which gives us for every part in the atmosphere where the cloud particles form, where they are moving to, how big they are growing, what material composition they are, how many they have, what feedback on the gas phase they have. Therefore, it's linked to the gas phase. And if time allows, or if our research question is in this direction, we also run our photokinetic gas phase chemistry. I'm leaving you with these words. I'm more than happy to say more about the details, but maybe this is good enough for now. Why are we doing this? We are doing this in order to physically interpret observations. And in astrophysical terms, that basically means we're solving the radiative transfer equation and producing transmission spectra, photometry, and phase curves in order to serve this space missions. And from now on, I'm moving deeper and deeper into the research, and you are more than welcome to put up your hand and say, can you say a few more understandable words? Yes, oh, there we go.
Yes, that's very noted question. So basically, on the pictures in the short earlier, we see exoplanets on the pretty much local neighborhood of the source.
That's true.
And then we talked a little bit about how we're trying to understand how characteristics of the exoplanets are going to depend on their star environments. But basically, solar neighborhood is still close, at least as far as, for example, Gaia can see. So we cannot really, and our modeling of Milky Way is, it is good in some aspects, but it's very far from being complete. So how can we analyze, how we can consider how the planet's properties depend on their environment if what we really can properly observe is just basically next door to us?
Well, if we are looking next door to us, we already find a metallicity gradient in the host stars. So and this is already a galactic environment effect. So this is one thing, so the metallicity, and this then affects the planet formation, and it definitely affects what we see. Because if we are running, for example, wave transfer, etc. The other aspect is, of course, then the radiation field, the external radiation field that the object is seeing. So if you know what is in the neighborhood, we have a much more profound external boundary. So these two things.
Okay.
Of course, I would love to go into no, actually I don't. I wouldn't love to go into the center of the galaxy, because there we only have high mass stars left, and it's pretty detrimental. So we're not going to do this.
What about effects related to the fiber structure, basically, something like remnants of the mergers and okay. I see.
Give me a merger, I give you a planet. I don't know. Galactic mergers?
Yeah.
Well, I mean, then we suddenly are back into small-scale gravitational effects on the planetary systems. I'm not aware that anyone put the small-scale effects in their galaxy merging simulations, because they are n-body simulations, right? So, and that's one billiard ball for each of them. Well, okay.
So basically, for now, let's stick it to metallicity and large-scale gravitational potential.
And the radiation field, and the external radiation field. So what else would you suggest? What else would you suggest?
Zero, I thought it next up. Just an outsider point.
Great. Okay. Good. So from now on, I'm dragging you deeper and deeper into our research field. So now you're aware we are doing three-dimensional global circulation models for atmospheres. We know pretty well how to do the cloud formation and the chemistry, which then helps us to make a prediction for how these planets actually should look like. But what we also, if we have a model, we also can make predictions, and we can do ensemble studies. And this is what I'm showing you here. This is a whole grid of models. So all of them, the basis of them are all three-dimensional simulations. And what we did, we cut them in the equatorial plane and plotted here the temperature map. So I'm showing you the whole set of models for just the equatorial plane. What? Yeah.
So what is the distance of the planet from their star?
That is a very good question. And the distance, let me just see. So we have there are two axes. The x-axis is the host star. So we are basically moving from M to F. And here we are moving closer and closer to the host star, such that this particular global temperature of the planet is reached. So that means they are not all at the same distance. They are at a distance such that this temperature is reached, which means the ones with the highest temperature are the closest to the host star, and they are easily just 0.9 orbital. They easily have an orbital period less than 1 day. Yeah, so they are very close by, and this is also why you see this huge diversity now. If you are far away orbiting a cold star, then we have a pretty homogeneous temperature distribution around the planet. The further we move to the host star, the more heterogeneous it becomes. And what we see actually here is that there is a huge temperature difference between the day and the night side. And that's what we're going to use to actually study then later on the magnetic field. Right. So, in order to characterize extrasolar planets, there is one working horse, and it's the so-called transit method. Probably most of you have heard about it. So here's the star, obviously. We are here the observer. Does actually someone recognize this this space mission here? Not? That's good. So this is definitely the sun, so that's our host star. And in the end, maybe someone realizes that. Come back to me and maybe you have an idea of what it may be. And the planet is moving in front of the host star, and we are staring at the system, right? And we can do this in different ways. And that's what I'm going to show you in a second. So what this means is we are measuring the flux out of transit, in transit, out of transit. It means the depth of the flux drop is equivalent to the size of the planet. But this size is wavelength dependent. So there are various ways of doing this. There is basically the whole disk integration, which gives us what people are calling the transit spectrum. What it basically means, we are doing the experiment of the transit at different wavelengths, and then we record the depth of the Verdunklung, this is horrible. The depth of this brightness drop. There we go, of this brightness drop. So the other one is that one can really time the observations very well, so that one observes only when the planet is moving just in front of the star and when it leaves just the star. And this helps us then to actually analyze what we are calling the morning and the evening terminator, which is very valuable because we then can get already an idea what the extremes of the planet actually are. And then we may observe at one wavelength, we may follow the planet orbiting the host star at one wavelength, and this is what we are calling the phase curve. And the fun of this is actually that we would naively expect that this phase curve is some sort of sinusoid, but actually it is not. And it's not because there is a hot spot offset such that the sinusoid is kind of a little bit tilted. So the instruments that we are seeing here is the missions. This is Cheops, this is JWST, and this is Plato. Now, with these instruments, we are already able to characterize extrasolar planetary atmospheres, for example, with respect to their shapes. Now let's go through this a little bit and see 15 minutes or something. Yeah, and see what makes this shape. So here we are again starting with our virtual laboratories, and I know it's a busy plot, but we're getting there. Up here we have the temperatures for 3 different climate regimes. These are the cold ones, these are the ultra hot ones. So we have temperature differences of up to 2,500 Kelvin would be the day and the night. And these are the intermediate planets. So they're intermediate because they get a bit crazy. If we go down here, we see actually characteristic properties for cloud formation. Here we see where cloud formation takes place. I'm taking this step by step. So, first of all, what shapes the observational atmosphere? We are observing, if we are doing the transit observation, we do see this part and this part of the atmosphere. And it's clearly, here we would see the same, and here we would see very different thermodynamic situations. This is hotter, this terminator regime is hotter than this one. So we should see differences. Okay. Yeah. Okay, yeah. So here, this is the experiment. Here's the star. Here is one of these simulations, and here we basically see this part and do the transit experiment. Okay. There you go. Because this thermodynamics is so different, here this side is much hotter than this side. This also has an impact on the chemistry. So here I'm forming much less clouds than here. So therefore we have another asymmetry in the atmosphere that we actually can observe. Why is this important? Because if I have a cloud forming, I can look less deep into the atmosphere. That means it becomes immediately clear that we could look less deep in the atmosphere on this side of the planet than on this side on the planet. Another asymmetry. And then it becomes crazy. Here we are showing the ionization. It's simple thermal ionization. We basically look at what the local degree of ionization is. If the local degree of ionization is above 1, the gas is completely ionized. If it's below 1, it's partially ionized. First of all, we again see in our warm planets, it's nicely homogeneous, meaning boring. But if we are moving here to our hot to our ultra-hot Jupiters, we see that the day side is completely ionized and the night side is completely cold. And this has implications actually for thinking about magnetic coupling. So if we have an ionized gas, we may have a magnetic field that affects the local atmospheric dynamics substantially, because suddenly we have the day side of the planet which is completely ionized, therefore, or is partially ionized, and therefore can to a certain extent couple to the global magnetic field, which then affects the local hydrodynamics. Okay. So what I wanted to do is I wanted to show you what we can use this models for with respect to observing using multiple instruments. So I have shown you our simulations. These are our virtual twins for various gas giants orbiting different host stars. Now we have also the A-type stars, and you again see the large diversity of this temperature maps. So, and I'm showing you now two observations. This is a so-called secondary. No, you don't hear me. This is a secondary transit where we are actually observing the reflected light from the day side. So the planet is moving behind the star. And we do this for various wavelengths. On the x-axis we have the wavelengths, on the y-axis we have the occultation depth, whatever that is right now. In the white dots are the observations, and the underlying lines are the models. And this planet, it's WASP-18b, is about this planet that we have models. And if you squint a little bit, you see that the golden and the yellow line resemble the observations enormously well. And what is actually more is that if we introduce a magnetic field coupling, our models fit even better the observations. And it's not fitting just one point, it's fitting the entire wavelength range from 0.4 to 8 micrometers. We have done a similar exercise for WASP-39b, and this is now a transit observation. This is a transit spectrum, what I mentioned earlier. Here is the entire wavelength range from the optical to the infrared, so these are 10 micrometers, and this is the transit depth. And here we are accumulating observations from different instruments. In green from the VLT, so it's a ground-based instrument, high resolution. Then we have in purple the HST observation, and in orange the JWST observation. And the gray line is the fit through our models. And you see that we are fitting from the optical to the infrared with one model, with one consistent model, all these observations. And I think this is a very nice success for our research group, and I'm really happy for our people. So let's see. I told you, no, I didn't tell you. One of the holy grails in exoplanet research is how to measure the magnetic field of a planet. Because we cannot just go there and stick a magnetometer on the surface. Yes, I did tell you. And we also cannot measure the Zeeman splitting of a local magnetic field line. And the reason is, of a atomic line. And the reason is we get simply too few photons. So, and what we did, we tried to use our models to backward engineer the whole thing. This is the same plot that you saw before, but I'm now showing you, I'm now zooming into this, and you see that the model with the magnetic coupling fits almost perfectly the observations, while the model without magnetic coupling doesn't fit it. From the physical background, this is again the degree of ionization on the day side, very relatively high, on the night side, very low. And this actually means we cannot simply do what our solar system colleagues so happily can do, is namely run a beautiful MHD simulation. Because MHD, an ideal MHD simulation, assumes I have a homogeneously, completely ionized gas. We don't. Yes?
I was thinking that the developer at the viewers will go collecting the heat with the atmosphere, it is all like the layers. How should we think about this? It's like a glass. It's down, like it's going on from the surface, the last one is just like this men in the last
So we have, yeah, so the white thing in the middle is the core which we are not modeling. So we are modeling down to 700 bar, and this is a gas giant. So we are not doing a rocky planet. So we basically, this thing, the pressure increases increases inward without it becoming immediately a solid. So it stays gaseous. So that means we are now modeling here the extensive gas atmosphere. And of course, we would like to go further outwards, but right now this ends at 10 to the minus 4 bar. And yes, it's odd, because it basically tells you we have on the day side an ionosphere which really reaches deep into the atmosphere, while the night side is completely unionized. So it's beautifully molecular hydrogen gas. And this makes it tricky now, right? If you think about magnetic field coupling, because suddenly you have one side of the planet which is completely agnostic about that there is a magnetic field, and then you have the other side of the planet which is basically coupling to the magnetic field, and the atmosphere is kept in place. So we have a non-ideal, non-homogeneous magnetic field coupling, which is a bit, yeah.
These are probably only planets which are tidally locked.
Yes. Yes.
Daytime, nighttime.
Yes.
Really like
Yes. Yes.
So, has anyone studied if they are not tidally locked, whether they rotate, then this becomes even more complicated if you have one side ionized and the other.
I think it's a wonderful question. I would love to do this. This is no, we're getting there. This is the first simulation which actually takes into account a non-constant magnetic coupling, which means we are taking into account that the degree of ionization changes, that the Lorentz force changes, that the frictional heating then changes. So these are real actual source terms in our equation of motion and in the energy equation. So, and you're absolutely right, I would love to do this. Yeah, exactly. So to just maybe come to an end, there's so much interesting stuff that is going on. So here on the middle column is basically the simulation without magnetic coupling, and you see that the streamlines gave. So if you fold this, you go around the planet. That the streamlines are going around the planet nicely, unhindered. But if you are now invoking this magnetic coupling on the day side, well, it's basically on both sides, but on the day side it becomes active. Then the material is transported polewards. It's not just kept circling around the planet, but it's transported polewards. And this is of course substantial if you are talking about observations. So I have 3 more minutes, and I want to be a bit fast, but I want to go. So maybe I just make that point. The next, as I said, the next big space mission for in exoplanets for Europe is actually Plato. Plato stands for planetary transit and oscillations of stars. That means Plato is actually addressing both the stars and the planets. How many of you have heard about Plato? Some. Okay, good. But few enough so that I can say this. So Plato will have 26 cameras, 24 normal cameras and 2 fast cameras. It has a measure of 2.5 times 5 meters and has a mass of 2,300 kilogram. I'm saying this because this is the mass we have to pay in order to get it into orbit. In Graz, we will run a Plato launch event. So if you want to make the ride to Graz, you are more than welcome, and we will have it probably in January whenever the launch is actually starting. So there are the science questions for Plato. So how do planets form? Is our solar system unique? We have discussed it at the very beginning. And do other planets exist where life may be possible? And one of the questions we actually had is, can we use Plato to observe weather on exoplanets? I don't have much time to, or actually I don't have any time to tell you this. If you go to our webpage, there is a news, and our press person has very nicely prepared a press release about a recent paper. And with this, I'm just jumping through this. Sorry, because I want to finish with something that I have been repeatedly asked, and that's machine learning. And why I want to finish with this is because I think it is important that machine learning is fantastic, but we need to work on the ground truth. In order to train a machine learning framework, we need to hone, we need to know our in-depth, we need to know our core competence, our domain competence. And our domain competence sits in this modeling. So in the 3D GCMs, which is this one, into the cloud formation, this is this one, and then into the radiation transfer products on the sand side. So in order to harvest machine learning, we need to do both. We need to develop our fundamental research. I have shown you magnetic coupling, then we want to go towards high energy chemistry or cooler cloud formation. We need to make sure we understand our basic physics. And so we did, and we tried one aspect of machine learning. It looks crazy, I'm just giving you the main points. We used an entire grid of 3D GCMs in order to train a machine learning, or several machine learning frameworks, and then asked the machine learning framework to replicate the temperature map. And it did beautifully, much more beautiful than we had expected. And this, of course, made us wonder, why was it so easy? What did we miss? And then we thought, okay, we need to test, we need to figure out, we need to find a way to discuss the quality of our results. And for astrophysics, this is, of course, chemistry. So how different is the temperature that does it matter? How different can the temperature be that it matters for the chemistry? And the other one, are the differences observable with our present instruments? Does it make sense? So I have a machine learning framework, it gives me some prediction, and I'm asking myself, how good is that quality? Can I trust it? And my trust test is the difference to the deterministic solution observable? And this is on the sand side. So, and what you should see, or you don't see, and this is the point, is there is a red and a blue curve up here. The red curve is our deterministic model, and the blue curve is you don't see it. And the blue curve is the machine learning model, and they sit on top of each other. And that means that the spectrum is so good that it cannot be distinguished by any of the existing instruments right now. But now, of course, I have shown you the best of these examples. There are also not so good examples, and this is why it is important that we get our ground truth right. Because we also tried this then I know it looks crazy, there's nothing to talk about here. We also did this for the cloud formation, and what we actually learned was the moment the data structure becomes complicated, or we haven't understood our physics or our chemistry properly, then also the machine learning has a problem. And for all of us who have done a bit of numerics in our lifetime, this resembles our experience with numerics, right? The moment we couldn't pose a decent physics problem in mathematical terms, our numerics would screw up. So and this is exactly the same thing here for the machine learning. And with this, I actually want to come to an end, and I have put up a couple of conclusions. I think the most important is probably here the column 1, so that exoplanets are truly global systems that are affected by their local and by their galactic environments, that exoplanets exhibit different climate states that are driven by their three-dimensional structure and cloud chemistry. And maybe I want to jump directly to conclusion 3, because this is then answering to the title of this talk, namely, JWST is probing the atmospheric chemistry. So we learned through James Webb Space Telescope a lot about which molecules exist in these atmospheres. Plato will allow us to probe the horizontal cloud coverage, which nobody had expected. HST, Hubble Space Telescope, ties everything together to high-resolution spectroscopy. But what we are really missing is a simultaneous multi-wavelength observation, so that we actually can combine the causes of all the observations we are making in real time. And with that, I thank you for your attention.
Thank you very much for a very interesting lecture. So we have time for some questions. There were some questions already in between that. So Alex already asked 2 questions, and I will be now, and then we'll back.
Hi, thank you for the talk. And I'm sorry to say that quality very long. Okay, you're not hot or cooking, you're not any tiny dogs. Yeah. And exercise.
Well, you know it from the age of the system. So you know what the age of the star is, and then if you have a planet, then you already know that it can be tightly locked. But you also can look at the orbital geometry, and if it's almost circularized, then you know it's tightly locked. So it's a dynamic argument.
Thank you.
Well, thank you. Thank you. It's already curious, and my question is about. Okay, thank you. So it's already curious that my question is about your last conclusion about recent simultaneous multi-wavelength observation. So I remember you said it's very theoretician, but still. GJST and HST are big and expensive surveys. Plato, I do not remember what is the budget, but it is on the smaller scale. Is it potentially possible to do this simultaneous multi-wavelength observations with like a constellation of relatively cheap, relatively small telescopes that will be put in the orbit and actually observe exoplanets in multi-wavelength regime? Or is it still science fiction at this point that we need something really big and really expensive and simple?
I don't think we need something huge and expensive. We have actually demonstrated that we could use something smaller. So it's absolutely feasible.
Thanks for great. So I was wondering, do we know if the gas have a split core, or can it also be like direct to that? And is that something that you can see them in a bad filter come from, or how does it impact filter?
These are all very good questions. This is probably what the Juno space mission may help us with for Jupiter. So if once we know what the interior of Jupiter is, we hopefully can use this to extrapolate also for exoplanets. So I think I owe you the answer.
So on those picture with the temperatures of the planets that I had, there was a few of them, I think, within the lower right corner that had, like in the center, it was red. That, yeah, in this picture, like, it's okay with the bottom right. In the second, it's white. I mean, it's white, but when we're talking about that, it's like a red and blue. Then I'm like, I think it's a circle. I go, yeah, and then it came out. What is that? Because like, if I understand it correctly, if we're talking about like, okay, I'm not going to compare it to our planet like Earth, but like inside, if it's more dense, when a gas gets denser, it's more both the molecules or atoms bump into atoms.
Yes.
Bump into each other more.
Yeah.
Get hotter.
Yes.
So how is that cooler circle?
Yes.
What is it?
Yeah. It's a very good question and very well observed. So the classical situation, you have spherical symmetric gaseous sphere which has an outer boundary. That means it loses energy. That means we would naturally expect a negative temperature gradient from inward outward. And this is what we are seeing in here, right? So this is our negative temperature gradient. But now we have an external heating source. And this is what we are seeing here now. So that basically means that the external heating source really matters for this part, but not yet for this part. And maybe we see this actually nicer here. Here it's more continuous, right? So this is really now, thank you. I hadn't spotted this, but thank you for pointing this out, because this is now making a very beautiful example for that we have two temperature regimes here, right? So this is what comes from the external irradiation, as we say, and this is really the classical temperature structure from inward outward.
Sure. And what body? Thank you for your talk. First, very interesting. I just discovered for myself is that there is different observations with day and night.
Yeah.
So we have this model based on Earth observations, but then we apply it to some gas exoplanets, or we also have some observations of our gas planets. How this model, like how does it work? I also can't really understand if its transition was when it was 10 or it was 9.
Let's see, do we have...
Where is this threshold?
Mm-hmm. I think what we want is that one, right? So, What is your question now? It was- Yeah, right. Okay, got it. So I think we are pretty clear on the very left column, right? The 800 Kelvin model. It's cold enough so that the day and night are almost equally covered with clouds. So if we are now moving to the right-hand side. Right-hand side? No, yeah, right-hand side. So we are moving towards an atmosphere which has an intrinsically hotter day side. That means thermodynamically, only the night side temperatures are low enough that materials can be thermally stable or clouds can condense. That means literally that the temperature on the day side is far too hot, so we are talking about thousands of kelvins, that the phase transition from the gas to a solid or whatever, a condensation can take place, or in even simpler terms, that any material can be thermally stable. So therefore we have this difference. And now we have the differences between the evening. So think that the atmosphere streams this way, right? From the day side to the night side. That means you are streaming to the evening and then to the morning. So you're transporting from the day side hot material to the night side. That means the evening terminator will always be, the gas at the evening terminator will always be warmer than on the morning terminator, right? Let's see. So here, this is the evening terminator, gas streams this way. It literally is moved from the day side to the night side, and as it moves, it cools down. It has a radiative cooling timescale. And on top of anyway. So, and on the morning terminator, we transport cold material from the night to the day side. So, and only if this material is still cold enough, cloud particles can form, or on the other hand side, if this is still hot enough, not yet cloud particles. Cloud particles can not yet form. Does it make sense?
What causing transformation is you can react like this, and we understand.
Yeah, we can. We see. Let me see what I see here. Yeah, I think this is the easiest way now. So we can resolve the differences between the morning and the evening terminator. This is now indeed a model, but we have this from JWST for WASP 39b. We actually have observations from the morning and from the evening terminator, and they are different. And we already see that there must be different cloud load, whatever that now means in detail. What we see is that the absorption features of carbon monoxide, for example, have different depths. And this already indicates that there must be different levels of cloud in there. So we do observe it, yes.
There is no function.
I absolutely agree, it's super cool.
Thank you. One more question.
So if we can reach and detect some of the clouds and Earth, is it possible also to detect some geothermal changes like volcanoes or something like that of this planet? And another question is also if there is some artificial lights, then can we be able to detect this? And when somebody from the space observing the Earth, probably they would know some of artificial lights. Is this possible in the future? They detect something like that?
Probably.
You mean light policy?
Yeah, like it would be.
Well, to be very blunt, our light pollution is annoying for us, but I mean we have so big it's so challenging to observe the atmospheres of rocky planets at all that the person or the species who see our light pollution must either be very nearby or have much higher sensitivities in their observations than we have. So, and one more thing on this. Everything we know about exoplanets is because we observe the star. We never really observe the exoplanet itself, right? If we detect the planet through the radial velocity method, we detect how the star-planet system moves about their common center of mass. if you are now doing this transit observations here, or even this separated morning-evening transit observation, we are observing the star, not the planet. We are always staring at the star, and suddenly we see the planet moving in front of it, oops, and something changes. And we see this, oops, something changes in different wavelengths of the star. The first question, volcanoes, for this, it depends now on the evolutionary state of the object, but I would think one should see that because you have an additional influx of sulfur, for example. I think we actually did an exercise with one of the students to see how much sulfur it actually needs how much volcanoes you actually need to see it in the spectrum of an imaginary rocky planet with an imaginary atmosphere. Yeah, that should be feasible. Much more than seeing light pollution.